Hello, guys. You guys. All right. So today this is session 2. Welcome to this session. We would continue with what we started the last time. This time around, we'll look at the chain rule, understand how we apply the chain rule, and get meaning into it. And we'll apply some more generalized power function rules. We'll also look at differentiation of special functions. There are certain functions that do not behave like the normal functions that you probably would have seen. And if time permits, we probably may try doing some partial differentials, depending on that availability. Okay, so let's get into it. Okay, so chain rule. All right, so Isaac, you have your hand raised. Is there a question you want to ask?
Yes, please. Yeah, sir, please. Is this class for group 1, please?
The new group that has been shifted to, yes, it's group 1. I get
because on our WhatsApp platform, the class rep was like it will start at exactly 10 a.m. please.
Who said it will start at 10 a.m.?
The class rep. So I think they are waiting for that 10 to join the class.
Okay, so please tell them that we have started the class. I said we will start immediately after that one. So how come you sent? Okay, so let's pause the recording. All right, guys. All right. So welcome to today's session. So we're going to, by the end of this lesson, I hope we will be able to all understand how to apply the chain rule. And we'll do more examples on the generalized power functions. We'll look at differentiation of certain special functions and partial differential or partial differentiation. But before we start, could we just do a little recap, my friends, to cast your mind back and let's see how we can. Yes, so someone to just give me just give me the answer for this one and let's see.
2x plus 3.
Perfect. All right, so then this one as well. All right, so who can also solve this for me? Then
S/2.
Come again, you said what?
S/2.
S/2.
Perfect. And the last one here. All right, let me make this one. Let me make it easier for you.
One.
Yes, who said one? Oh.
1/s.
Yeah,
So it's 1.
It's 1. This is the same as x squared. Okay. All right.
1, yeah.
Yeah, so this is the same as x. You take the differential, it's this. Okay. All right. Okay. Wow, that's perfect. So, my friend, you said 1. What's your name?
Edward.
Edward. Let me get my Excel sheet. Just a moment. Put your name down.
Hello, sir.
Yes.
Sir, please, just so that the class will be complete.
Yes, please.
Can you actually confirm the mode of, because I think we are supposed to key in our name.
Yes, please. Yes. But this, Edward, what's your name in full?
Edward Safo.
Edward Safo. Okay, so Edward, you have 1 mark. Okay.
I see.
All right, so guys, please in the chats, I encourage that you write down your name and student number, okay, for attendance purposes. Okay, please. All right. Okay, so we have. So now, thank you. The chain rule. Oftentimes, when you have what we call a nested function, or we have a function within a function, and you're interested in dealing with search functions, we apply the rule we call the chain rule. So for instance, you have a certain, the easiest of it would probably you have a certain function that has another function that's this. So there is an inner function, let's say x plus 4, okay, and there is an outer function. So this is like the outer function, and this is like the inner function. Okay, so you have this and you want to solve functions like this. We apply something we call the chain rule, okay? And the chain rule says you try to get dy dx, let's say you have, so like I was given x plus 4 to the power 7, you have something like this. You do, so this is f of x, or let's say y equals something. And so to take dy dx, you have to first get dy du times du dx. So let's understand what this dy du means. So to make life easy for us, so we always try to bring the functions to a certain form that will be easy to apply. So if you have, let's say, a function x plus 4 to the power 7, we can take the inner function and represent it with u. So we say let u be equal to x plus 4. Now, once you've represented the inner function with u, what you have done is to rewrite, is like to take away this whole thing here, this whole expression here, and represent it with u. And then you add the outer function. Now, this ends up looking like a very simple power function where you can just easily solve for, okay? And so it says that if you do this, then you can do dy du, okay? And then you can now do du dx. So this function here, which is y equals this, is the same as this. So here we can do dy, okay, du. And then you can multiply it by the du dx. Now we have represented the inner function, this one here, with this. So once you have done this, you can also take the derivative of this one here, which is du dx. And once you do the two together, you would have found the derivative of the expression. And so here, dy du is to say this is like the power. So u to the power 7, all you have to do is to say you have 7 comes out, multiplies u, and we knock down the power by 6. And we multiply it by now du dx. What is du dx? Du dx is to take this derivative of this one. So this is going to be 1, right? So once you're done, you just back substitute your stuff into it. So this is like 7. And what is u? U is x plus 4 to the power 6. And all this multiplied by 1. We don't need to. And so this becomes the derivative of this function using the chain rule. So that's the idea. Now, it's called a chain rule because you can have a function within a function within a function, okay? So that when you have these kind of functions, you keep representing, and you break down all the functions or all the nested functions, and then probably you try to resolve them. All right, so Janet Barton, you have a question, please go ahead.
Sir, please, you are rushing.
Right, so if you have a function, let's see, x cubed minus 1 to the power 7 with respect to, so we want to take the derivative with respect to x. All right, so what we do is, so given the same idea, if we want to find dy dx, the first thing is to try to do our dy du, and then the next one you will do your du dx. So first you identify the inner function and then the outer function. So this is the outer function, something to the power something. So that's the outer function. And then the inner function is what you find in the bracket in this case. So we let u let u be equal to x cubed minus 1. Okay, and so if this is the case, then we can rewrite our function with y equals u to the power 7. And so with this instance, we can easily do dy du, which is the first one. So dy du in this case here is to take the derivative of this function here, and that is 7u to the power 6. And then we now multiply it by du dx, which is now, this is du, we differentiate with respect to x. And so here we will have 3x squared. Okay, so once you're done, you can again back substitute, and you have x cubed minus 1 and times 3x squared, and it gives us to the power 6. Sorry. All right, so then this becomes the derivative of this function given using the chain. All right, so let's take an example, a real application example of this, and then solve it together and try and understand what this means. So it says a manufacturer determines that M employees will produce a total of Q units per day, where Q is this. So Q is defined as this expression. Let R be revenue. Let R be revenue. Now, if the demand equation for the product is P, the demand, yes, is P equals this. This is the demand equation. Determine dRdM, which is the rate of change of revenue with respect to change in employees, also termed as marginal revenue product. So we have two different functions. You have function with respect to Q and a function with respect to P. And you're being asked to differentiate the RTM. Okay, so it's like we are crisscrossing in a certain sense. Under normal circumstances, we would have to do the Q dm and then probably do the P dq to get the RDM. Okay, so this is it. You have to get dr dm, we need dr dq and then dq dm. Okay, to get our dr dm. So let's go over gradually and see how this works out. So first, we have to find, we are interested in revenue. We've been given the quantity, okay, but this quantity is with respect to number of employees or the units. But here we've been given the price, okay, the demand function, which is the price. So total revenue here is always price times quantity. Okay, so if you have 1,000 minus 5Q, this represents the P component or the P element in the total revenue function. So we multiply this by Q and we have a full total revenue function, which is 1,000Q minus 5Q squared. So this becomes our total revenue function. So with this, we can do dr dq, okay, which is here. We can have dr dq here. And then we also have our Q here, which is the total units produced with respect to the number of employees. So we have Q with respect to M. So here we can also have the Q dm. And when we are done, we multiply the two and we end up having our derivative. Okay. So let's take the first one. So we have our total revenue function, which we found as I think 1,000Q minus 5Q squared. And this is TR. So TR, dQ, so we are differentiating total revenue with respect to Q. And so this would be 1,000 because it goes away, Q. And then this 2 multiplies the 5, which is 10, and we knock down the power by 1. So we have 10Q. Okay, so this is our dr dq. Yes, dr dq. Now, we have dr dq here. Then the next thing we'll probably also look at is, okay, well, so let's complete this. So we have Q, but Q is been defined as 10m squared plus 1 to the whole squared. So we can rewrite this the same as 1,000 minus 10, and then wherever we see q. Okay. Now the reason is that at the end of the day, we are looking at dr dm, and so this will now be, this is now with marginal revenue product, marginal revenue, which is encompassing the components of the number of employees in the situation. All right, so now let's look at the QDM, and that's like taking the derivative of this function here, QDM. All right, so you have 10 m squared plus 1 whole squared. Now this function looks something similar where we have a nested function. We have an outer function and then we have an inner function. So this is more like a function begging you to use the chain rule. So we take the derivative of the outer function, okay, multiplied by the inner function, which we don't get to do anything about, if you remember how we went about it. So we knock down the power by 1, and now we would now do multiplied by the derivative of the inner function. So this is going to be, this 1 goes away, so this is just going to be 20m. Okay, so everything here is, when you're gonna have 40m squared plus 1. Okay, so that gives us dq dm. So we have two functions. This is dr dq and this is dq dm. So we multiply these two functions together and we end up having our dr dm. And so that's it here. So we have the function here, which is dr dq, 1,000 minus 10m, 10 into bracket m squared subtracted squared. This is this part, so we'll call this dr dq. Okay, and then this one here that we found here is dq dm. So we multiply these two functions. Now, you take this, everything here is 1.
Hello, sir, please, we can't hear you.
Oh, really? It's the network. Hello? Hello? Hello, guys. Please, is it better? Hello? Please, is it better? All right, please, is it okay at the moment? Hello, guys. Please, is it okay?
Yes, sir.
Yeah.
All right, thank you.
Yes, okay.
All right, okay. So,
Sir, please, I sent a message in your DM. Can you check?
come again. You have sent a message in the chats. So please, which message? I don't really get the message.
Sir, please, it's a direct message.
All right. So, okay, there's so many messages there. I'll take time and go through it. All right. Okay.
Basically,
So,
say like,
all right. So we try to put these two functions together. So we just basically do a little expansion here. You take this 1,000. Now, please note that this whole function, this thing here is just one composite function. It's one function together, okay? So you take 1,000 and 1,000 multiplies everything here. So this is to say, let's say the 1,000 can multiply the 40m, and that is 40 million. Just keep this as it is, okay? So 40m into brackets, all this. There's no point in expanding everything here like that. And then you also take this here and multiply everything that's in here. So minus, the negative applies to everything here. So minus 10 into bracket 10m squared plus 1 all squared will multiply everything here. So the minus 10 times 40 is minus 400m. And then this here, the one in the bracket, 10m squared plus 1 all squared multiplies 10m squared plus 1. So because this is squared and this has an indivisible power of 1, the power goes to 3. Okay, so once we have expanded everything, we have this expression here. Okay, so this here gives us the derivative, which is dr dm. Okay, if we probably were given the value of m or know the number of workers in a week, we can easily determine that rate of change. Okay. All right. So we're going to apply more of the generalized power rule. Yes, Prince Tivia, you have a question?
Sir, please, I don't really get it. Can you come again?
You don't get what? You should be specific. You can't just say you don't really get it. So tell me what exactly you don't get, then we can all help understand. But the moment you say you don't get it, should I go and start the whole lesson again?
The RDM.
Yes, so what, so let's go back and start again. So what exactly don't you understand? So the question is asking you to find the RDM. So tell me what exactly, which ones have you understood? To what point did you follow to, and to what point did you lose the lesson? Yes, I'm listening. All right, so Kwabena also Nemo, you have a question, please.
Sir, I didn't get from the DQDM list. I don't get how we got 20, a 40 over there.
Okay, so you understand going back to the, what's it called? Yes, in getting the chain rule, okay? In understand in getting, what's it called? Oh, where is it? Good, perfect. All right. So if you have a certain function and maybe y equals something, let's say x squared plus 1 or something. To get this dy dx here, it is not that easy. We can just easily get dy dx here. So we kind of like rewrite it to establish a function or relationship between two different functions. So first we identify the inner function and then the outer function. And so we say let u be equal to the inner function, which is x squared plus 1. Okay, right? And so once we have this, then this y here, which is all of this, can be rewritten as y equals u to the power 7, right? So now to get dy dx, it is taking the derivative of this function times taking the derivative of this function. That's why we have dy du, which is with respect to this one. Then you multiply it by du dx, which is this. And then when we put all this together, we have dy dx. Okay, so that's the same thing we're trying to put across here. So we have a certain function. We have, say, this q. Q here represents it says that the manufacturer determines that M employees will produce a total Q units per day. So this is quantity with respect to the number of employees. So Q equals 10M squared plus 1 squared. Then it says also that let R be revenue. If the demand equation for the product is P, guys, could you please mute the fellow? Now, so if R is revenue, okay, let R be revenue. If the demand equation for the product is P equals this, so we have P is 1,000 minus 5Q, okay? Determine the RDM. Okay, so now we have been given something related to revenue and something related to employees. So it's like we are crisscrossing. We are kind of like, you want to combine these two equations, okay, to kind of have our DRDM. So DRDM is now going to be taking the derivative of the revenue function and then also the derivative of this output function with respect to employees. So it's like saying here we will do, let's say, this is revenue. So we can do dr dq. Okay, so we would have to find the revenue expression for this. So once you have this, this becomes total revenue. So we have dr dq, and then we'll multiply it by here. We will have dq dm, right? So we are going to take the derivative of this with respect to m. Okay, so more like dq dm. Now, when we put this and this together, then we will end up having dr dm. Okay, so this is all we're trying to put across. So now we're just going to take this separately and take this separately, take their derivatives, and when we are done taking their derivatives, we put them together like we have here. Okay, all right, so so let's start with the first one. So let's take the first derivative here. The first one is, let's find the total revenue expression, which is the R, the revenue function. So we have the equation we were given was 1,000 minus 5Q. And 1,000 minus 5Q, this only represents P, the demand function. So when you multiply it by Q, because we know total revenue is price times quantity. So when we multiply this by Q, we have a total revenue function. So we have 1,000Q minus 5Q squared. So once we have this, it is possible, now that we have total revenue, we can now take the derivative of total revenue, which is dr dq. Okay, it means we are taking the derivative of revenue with respect to quantity. Okay, all right, so we take the derivative here, and you have 1,000 minus, this would be 10, and knock down the power by 1. So we have 10 minus q. Okay, perfect. Now, the only thing is we already have, what's it called, the q that has been redefined here in this expression. Q is defined as this. Okay, so when we have q in our function, we just, wherever you see q, you substitute q with that expression 10, 10m squared plus 1 whole squared. Okay, so our revenue function, our marginal revenue function is this. Now, the next one we want to look at is the Q, the M. Now, the Q, the M is to take this function here. This is the Q, and with respect to M. So here we don't do anything. So we have a function which is 10m squared plus 1 all squared. So let's take the derivative of this function. So let's take the derivative, which is the Q. So this is Q equals this. So let's take the Q dm. Now, with this function here, we can take the derivative of this function using the chain rule. Okay, now if you want to do it just like I taught you at first we can take the inner function, so and let the inner function be equal to u. So let u be equal to 10m squared plus 1. Okay, and then so then the outer function will now look like y. Sorry, so now it is going to be q will be equal to u squared. Okay, so when we take the derivative, we are going to take the derivative with respect to this and derivative with respect to this. So here, this is going to be 2u, okay, 2u. Now, then now we now multiply it by the derivative. So now we'll now do du dm. Okay, and here, this is going to be 20m. Okay, and this one goes away. So when you back substitute, you're going to have 10m squared plus 1 times 20m. Okay, and we just trying to tidy up this to make it look awesome. So what we have here, 2 times 20 will now be 40m into bracket 10m squared plus 1. Okay, so now we have our dr dq, and then we also have our dq dm. So we just multiply the two, and then we have our function. Okay, so this is our dr dq, and this is our dq dm. So let's put them together. So we take this here, dr dq is this 1000 minus 10 into bracket 10m squared plus 1 whole squared. This is it. Okay, then we now take the second one, which is 40m into bracket 10m squared plus 1, which is dq dm, which is this one here. Okay, so once we are done, we just multiply the two and have the simplest form of it. And then once we do that, we are done. We are just kind of like simplifying it in some sense. So I take this function here, this 1000, I multiply it with everything in the second bracket. Okay, so this is 40,000 m, 10m squared plus 1. Then this minus sign here is this. Okay, and then I take this 10m, this 10 into bracket 10m squared plus 1 all squared, everything here, and I multiply it by everything here. To be on the safer side, just multiply this with this, and then what's in the bracket, you also put them together. They are like terms, they're the exact same thing. So 10 times 40 is 400m. Okay, or minus 10 times 40m is 400m. And then 10m squared plus 1 all squared times 10m squared plus 1 would be 10m squared plus 1 cubed. Okay, so at the end of the day, when we put everything together, this is the final answer we have, okay, from the basic expansion. Is that okay? Do we all get it? Yes, Vanessa Kubo, please go ahead.
Good morning, sir.
Yes.
So please, my connection was a bit distorted, so I didn't get the last derivative. That's the 40,000 m into bracket 10m squared. Could you kindly elaborate on that, please?
40,000 m. We just we multiplied these. So take 10, 1,000 multiplied by everything here. So this is like saying you're doing 1,000 times 40m. Okay, all right, so take this, this multiplies everything. This guy is already multiplying everything here. So 40 times 1,000, this is just 40,000 m. And you just keep everything as is. You don't have to stress yourself to expand anything. That's how come we had this one here. Then you take this one here, this 10m squared plus 1 all squared, okay? And you multiply it by 40m 10m squared plus 1. Okay, so you take this here, look at this 10, look at this 10. They are the exact same thing, the exact same thing. So all we need to do is just multiply this and this. And we have 400m and just 10m squared plus 1. Now, this has a power of 2. This has an invincible power of 1. So we just cube, okay? So you have this, and you have that, and you're done. Okay, all right. Okay, so we have the generalized power function. So again, when we apply this concept, it's not different from what we are doing anyway. Yes. So this is more like we are going to apply more of get some more examples of the generalized power function rule. You please mute the someone has left their microphone unattended to. It's giving bad feedback. Okay, all right. All right, so sorry. All right, so it is given a function y equals something to the power p. The derivative with respect to this can be obtained using the general formula. Okay, so I think it's the same thing. The p. Okay, so normally we added this slide because the shortest cut to doing what's it called, chain rule problems, when you have, let's say, something xn plus 1 to the power p, I normally just tell students that, you know, differentiate the outside function. Okay, so take the derivative of the outside function, leaving the inside function as it is, and multiply it by the derivative of the inside function. So this, what you have here, let's say the p here is the outside function, and then what you have inside is the inside function. Okay, so first take the derivative. You just assume, like, cover this thing up. Just assume like this thing is not there and it is only a bracket and p. Okay, and so once this is not there, you can just have your p, okay, and then the bracket, so this p minus 1. Okay, and then once you've been able to do that, you bring back whatever p, whatever is in here, and then now multiply it by the derivative of whatever is in here. So you have nx n minus 1. Okay, then you have your expression. Okay, however, I think I didn't teach it. I didn't teach that shortcut that way. So I went through the process. So this slide is, at the moment, it's the exact same thing I just taught. All right, so it says we have certain special functions that when you have to take the derivative, they behave a little different from the normal ones that we see or we have. So let's say if you're taking the derivative of a natural log, okay, again, using the chain rule, this is more like an inside function and an outside function. It's an inside function, outside function, inside, outside, out, in. Okay, so you have to take the derivative of the outside function. So yes, just no, hold on. Hi, I mixed it up. This is the outside function, the outer function, and this is the inside function. Please forgive me. All right, so you take the derivative of the outside function and multiply it by the derivative of the inside function. Okay, so when you have the natural log of anything, it is 1 over whatever that thing is. Okay, so we say if you have a function, let's say natural log of x, let u be equal to the inside function. Okay, like we have seen. And so this is the same as y is natural log of u. And so the natural log of u is 1 over u. And then we now multiply it by the derivative of the inside function. You please mute the fellow. All right. All right, and then you now multiply it by the derivative of, so you multiply by the derivative of the inside function, dy dx, okay? So, and it just works straightforward. So for instance, we have this function here. We'll look at some other ones. Natural log of x, okay? So here, we let x, okay, so I guess this is the same thing we have done. So we have this here, and you say u will be equal to x. So the initial function is just going to be 1 over u multiplied by, now du dx, if you have x here, you want to take du dx, this is just 1, okay? So all you have is 1 over u. And then we know that we have to back substitute, so everything is 1 over x. Now, whenever you take the natural log of any function, you're only going to have 1 over that function. Take y equals natural log of 5x, okay? And you apply this concept here. We say let u be equal to 5x, okay? So our function y will now be ln u. So you're going to have 1 over u, okay, multiplied by, now we need to have du dx. So du dx is 5. Okay, when you take the derivative of 5x, that's 5. So this is the same as 1 over 5x times 5. And this multiplies that, and you're going to have 1 over x. Okay, so it just, and these are some of the things that make these kind of functions that special functions. All right, so we have a function, say y equals the natural log of x squared plus 5 all squared. I love this because this is a typical example of a chain rule. This is a function, and this is a function, and this is another function. So it's a function within a function within a function. These are nested functions, 3 nested functions. Okay, so, well, let's see how it works out first. So we say this initially, this would be, okay, our outer function, and this would be the inner function, okay? In this sense. So let u be equal to the inner function, which is x squared plus 5 whole squared. So all of this is being represented by u. So then our whole function would now be y equals natural log of u, okay? So if we have to take the derivative, then we know that we have to take, it is going to be, the first one, we will take dy du, and then we'll now do du dx. Okay, so dy du here, in this case, is now going to be 1 over u. Okay, that's the first one. And then to do, so this is dy du, okay? Now, the next thing is to do du dx. Now, to do du dx is it looks like this is not a normal function you can just eliminate. So again, we have to now, if you want to follow the chain rule, you have to represent this by something and something and all that. But well, I think by now everyone has a hint of what the chain rule is. So take the derivative of the outside function, which is 2, okay? And keep the inside function as it is, squared plus 5. And multiply it by the derivative of the inside function, which is, in this case, we have 2x. Okay, so we have done this here. So this is du dx here. So if we want to put this together, 1 over u times du dx, which is this. So you have 1 over U is x squared plus 5 all squared multiplied by, let me just simplify this. 2 times 2x is 4x. So we can make 4x x squared plus 5, okay? So this guy can sit on this, it's very easy. Or this, all of this can cancel all of this because this is squared, okay? So all we have left is 4x over x squared plus 5. And you have your final answer as this, okay? Very straightforward stuff. However, we also have some laws of log that we can also apply straightforward to this kind of stuff. It says that, well, in terms of log, log, we oftentimes are not oftentimes, in log, we deal in bases, not in exponents. Okay, so when dealing with stuff that have exponents in log, we can just draw out the exponent, okay, out of it and deal with the function itself, and just, you go straight forward back to your function. So for instance, if you have a function natural log of x squared plus 5, and we are supposed to deal with this in log, another way of writing this would be take this power, take it out, which is 2, the natural log of x squared plus 5. Then you can just solve this using the exact same stuff here. With the chain rule, this is the inside function, outside function. So this is, you can represent all this by u, and you have 1 over u multiplied by the derivative of the inside function. And here it is just going to be 2x. But bear in mind that whatever the case is, we already have the 2, which is outside this one here, like this. Okay, so you just have to back substitute 2. This guy sits here, so you have your 4x over u. And we know that u is x squared plus 5. And so then it gives us straightforward what our final answer is. All right, so we also have another function as this here, that you have the natural log of x squared plus 2 to the power minus 1. Well, again, you can use the log approach by just drawing the minus 1 out of the equation and just go ahead and just solve, or you can just solve it with the same approach, okay? Either way, I'm sure you are still going to be very correct anyway, and you don't lose anything. So let u be all of this, which is the inside function. And so we know that du dx is all of this. So we take the derivative of the inside function here, which is this, all of this. So you only end up getting minus 2x times everything in this expression. And then the outer function is 1 over everything, so 1 over u. So we have 1 over u multiplied by the derivative of the inside function. And so we end up having this, and then the final answer is minus 2x over this. And it works just easy. So either ways, it works just fine for you to just look at the approach that easily works the best for you and just apply it. It's math. Once you apply it and you arrive at the thing, everyone is fine. Okay, so we also have another special function, which is the exponential function. For the exponential functions, when you take the derivative of the exponential function, it is the same. It is the same way when you take the integral of the exponential function, it still remains the same. Okay, so when you have a function y equals e to the power x, y prime of x is the same as e to the power x. These are some of the things that makes this kind of function special. The same way that when I said when you have a certain function, the natural log of a certain function, natural log of x is the same as 1 over x. Okay, it just These are the things that make these functions. Okay, and we also have the logarithmic functions, or in the general form. So when you have log base a certain function, it is just 1 over the natural log of the base multiplied by the function times du dx. Now that's just saying, so whatever the function is, you remember, we represent this, we'll call this the inner function. Okay, you represent the inner function with u, and you just take the natural log of the base, and then you multiply by the derivative of the inner function. Okay, so let's try some examples and see. So here we have this function, say y equals e to x. Okay, so what we're trying to do here is to say that, well, so this is the outer function, this is the inner function. Let the inner function be equal to u. So let u be equal to the inner function, okay? So that our y will now be e to the power u, okay? So if this becomes the case, then this is the same as, now we're going to take the derivative of the what's it called, the outer function, and multiply it by the derivative of the inner function. So this is eu, okay? Because for this, when you take the derivative of the outer function, it's still the same, and you multiply it by the derivative of the u dx. So you find dy du multiplied by du dx, and du dx is, when you take the derivative of x, is 1. Okay, so 1 times this is the same as eu, and you just back substitute, so e to the power x. Okay, so now let's take a more realistic one. E to the power x squared plus 1 all squared. Guys, could you please mute the fellow? Wait. All right, so we have a function y equals this here. Now, so outer function, inner function, okay? Inner function, outer function. So let u be equal to the inner function, okay? So our y will be equal to e u. So to solve this, like the chain rule, we have, you take the derivative of the outer function, leaving the inside function as is, and then multiply it by the derivative of the inner function. So here we take dy du, okay, here. So dy du is the same as eu, okay? And then now we will multiply it by du dx. Okay, so we have to multiply this by du dx, and so how to take the derivative of du dx is that now you take this. This also is needs a chain rule kind of approach. Okay, so just be careful. But now I think everyone is okay with it, so we can easily. So we take the 2, bring it up, and then we keep the inside function as is, and we multiply it by the derivative of the inside function. So the inside function is, this 1 goes away, and we have 2x. Okay, so this is our expression. However, we have to back substitute. So we have e to the power x squared plus 1 all squared multiplied by, oh, we could just make this guy easy for us, make 4x and x squared plus 1. So that gives us the final answer. How's this? Okay, so let's see. Last time I gave a question to your friends. I am hoping to find it so we can all, you guys can also try it. So could you please pardon me, give me just a moment, a short one. Try to find it. Okay, so you guys are not lucky. I can find it. I was hoping you guys could have a try at it or have a go at it. Oh boy. All right, so well, I guess I'll try and find it. When I do, I'll probably find a way of getting it to you. Okay, just stuff for you to also try. Get your hands on. Okay. Okay, so first for a startup, well, these are all past questions that I have checked. So s squared plus 5 squared. So someone should solve this and tell me what the answer is. Quickly. Anyone? Yes. Anyone?
4x over s
Has
squared
to
plus
be
5.
4s over s squared plus 5.
I found this very interesting question. I didn't write it down, unfortunately. All right, you guys, I'm sure I'll find this for you. It's one of these exponential questions, and then we probably will try. We'll get our hands on it and solve it together. Okay, all right. So, well, but let's try it. Let me see if I can. So I can have e to all right. So can we try this as a team anyway? But first you try it first and let's see how this goes. Okay, so let me make it nice. Perfect. Has anyone been able to try something on it? Anyone? Yes. Adenyo.
Okay,
Yes.
so I'm not quite sure. Just try.
Yeah, don't worry. Even if it's wrong, you get -5, so no problem. Just go ahead.
So, sir, I'll be having e raised
You
to
will
the
be
power.
having or you have.
I have
Okay.
e raised to the power, the same thing, root of s plus 1, multiplying half, exponent half, like the same question. Okay, yeah, that's it. Multiplying 1 over 2 into bracket s plus 1 squared. So meaning 1 over everything that I'm about to say.
Okay, please. So you have e. You say you have
yes.
e.
Root of s plus 1 multiplying
1
over 2 into bracket s plus 1 squared, all squared.
Guys, do you agree with that? Okay, so
No, sir.
I see more
No,
hands
sir.
are being raised. So please,
No, sir.
please, give me her name, okay? You know what is I know I remember the note, so I'll find the name in the list. -5, okay? So when I have your 5, I can share it to other people, so I can easily give me 1 mark. All right. So those of you shouting no, say no, say. Make sure yours is correct, because if it's not correct, yours will be -10. But it was so easy for you to to shout that someone's answer is wrong. You think it will make it easy on you? All right, okay. All right, yes, please. It's okay. It's a joke. It's I'm not serious about it. Okay, yes. So let's go.
So I have. So please, can I talk?
Oh yes, please go ahead. Yeah. What's your name, please?
Okay. So Israel, sir.
Israel. Okay, yes, Israel.
So please, I have e to the power root of x plus 1
E to the
multiplying x plus 1
multiplying.
x plus 1 all over 2.
Is that all?
Yes, sir.
Okay, perfect.
So let me try.
Yes, please try.
Okay, so I have the power root of x plus 1 multiplying x into bracket x plus 1.
X into bracket x plus 1.
Yeah.
Is that it?
No, x multiplying. Yeah.
Okay. All right. So could you give us a framework of how you solved it?
Okay, so
because this is straightforward, something you guys could easily
okay, let me try. I did it in a way. So you see, e to the power into bracket x plus 1 bracket close to the power 1 over 2.
Okay.
Multiplying the derivative of the u. Okay, so I'm going to get 1 over 2 into bracket s plus 1. Multiplying. Okay, s plus 1.
I have
Say.
So now you are seeing the light.
The second one is the correct one.
Okay, so you're all seeing the light. Okay,
Yes,
so
Yes,
all right.
yes.
So like I always try to tell you for my friends, I know some of you are okay. You can easily just deal with this, but just try to rewrite stuff in ways that would make life easy for you. Okay, so if you have anything under this root, it's the same as something root to the power 1/2. Okay, once you have this 1/2, you can easily take the derivative of this without stressing yourself. Okay, so here you can have, so at least we know that the first part will be the same. The only thing is about the second part. We taking the derivative of this one. So let's try and take the derivative of this one. Okay, to the power 1/2. Okay, so when we take the 1/2 comes to multiply everything here, okay? And because this also looks like something in the chain rule, so you could just leave what is inside as is, and then multiply by 1. Is that okay? But you, the power here, this is 1 over 2 minus 1, okay? Okay, so normally I like to do this, just make it 2 over 2, because it's minus 1 there. And so this is for my friends who don't like fractions. Okay, so this will go into this 1, and this will be minus. This is also 1, isn't it? Go into itself 1 and multiply this 1. Okay, so this is the same as negative 1 over 2, isn't it? Yes. So minus 1 over 2. All right. So you don't need to do anything else again. I thought I would have preferred this lady would have just taken
Yes,
out.
so I made a mistake.
Yeah, you
It's
just
supposed to be
taking out.
power of half.
Exactly. You just take this thing out and put it to power of half. That's how you multiply it by this. That's how. And okay, and then this one is also close a little bit, but you ignored 1/2 minus 1.
Yes.
You still need a little bit of the power here. Okay, that's one. Yeah. That's all. And then and for this one, that's why for this one, I was very curious. That's why I asked him to explain how he got it, so that we are sure. So if anyone must get a -5, it should be this guy, isn't it? And this is Israel. Israel gave this answer, isn't it?
Sir, no.
Israel, when
So Israel gave the first one.
Sir, I was the one. I'm sorry. I made a mistake somewhere.
Okay, all right. You are fine. I like how you just accept it and just make it. Okay, so -5 for Israel and -5 for.
Hey, sir, I wasn't the one.
All right. Okay, guys. All right. So that's okay. So we are all. I like the fact that we are all getting. Okay, so let's do one last application question and then call it a day. Okay. So we would apply the idea of chain rule in the case of elasticity of demand. Now let's try and those of you who have taken a little economics, there is a concept we call elasticity. And elasticity tells us the rate of change or the percentage change in quantity demanded as a result of the percentage change in price, or the percentage change in percentage change in quantity as a percentage change in income. Okay, so we have income elasticity and then price elasticity of demand. These are concepts I know you were taught just last semester in economics. If anyone says it's a lie, they should tell me so that I go to the finance department and go and ask. All right, so we say so we know elasticity is a percentage change in quantity over the percentage change in price. Okay, so let the percentage change in quantity be the Q, and then the percentage change in price, we want to call it the P. Okay, so then we know that if we do this percentage change, the Q divided by the P, okay, because we know it is percentage change in quantity over percentage change in price. So if this is percentage change in quantity and this is percentage change in price, we are dividing them. So if we can't deal with this, so we have to transform it sort of. So this becomes P over PP, okay? And if these are multiplying each other, we can easily just group like terms, just put the dP's to their side, one side. So this is the same as say we have dQ dP times P dQ, okay? So it's just a basic expression here. And just notice that this quantity is with respect to P, okay? So we can, this is like, normally you notice that when you're being given the quantity, you're giving it in P, or maybe the demand function of something is P equals something, but it's with respect to Q in some sense. So just notice that here, this is quantity with respect to P. All right. So suppose that we have something like this. So this example, typical example, what I'm saying, this is that the demand function for a product is Q equals this, but you notice that the variable, it is with respect to P. That's how come we say Q in the expression we wrote P, Q with respect to P. All right. So Q, P squared minus 40P plus 400. It says find the point elasticity of demand. So we have this expression here, and we are to find the point elasticity of demand. And we have derived the expression that is the Q, the P, multiplied by P over QP, okay, which is saying quantity with respect to price. Okay, so what is the Q dP? The Q dP is you take the derivative of this expression here. And the derivative here is this 400 goes away. So this is like 2P minus 40. Okay, so this is the QDP. We multiply it by P over Q. And so we don't know what P is. We've not been given P, but we've been given Q. And Q is P squared minus 40P plus 400. So we divide everything by P. That's all. So this is expressed as 2P squared minus 40P all over P squared minus 40P plus I think 400. So given this expression here, this expression here, or what we have here, or what you see here, is the point elasticity of demand. If we want to calculate the point elasticity of demand, so at any point along our range, our demand range, given this expression, we'll find the point elasticity. So for instance, it says that supposing P, so supposing P is 15, so supposing that we are demanding at 15, the price is 15. Then if you substitute 15 into the expression, then the point elasticity of demand we have here is -6. Now, you know, elasticity, we have elastic demand, we have the inelastic demand, and then we have the unit elastic demand. So when it is a negative value, when the elasticity of demand is negative. Geez, could you please mute the fellow? All right, so when elasticity of demand is inelastic, it means it is negative. When it is elastic, it's positive. Inelastic means that when there's a change in price, the change in demand is very insignificant. So in this case, we have a negative coefficient. And so here our demand is inelastic, and normally commodities with inelastic demand are those necessities like water, food, those kind of products that do not have substitutes. So when you get in there, you need to buy. If your car uses petrol, or you have petrol in car, you can go and buy diesel into it. You can go and fix gas unless you probably change the system. So then in that case, it's different. Yes, and Bernardine.
Yes, sir. Sir, please, I don't understand the formula A. Can you please take it again?
Oh, for the first instance, we are what exactly don't you understand now? Let me know what you don't understand before I can.
So the other side, the second side of the formula, the P over Q multiplying P, what are they representing?
P over Q multiplying P. Okay, so this one, you mean this side, right?
Yes, sir.
Oh, so let's start again. So we're saying that we want to find the price elasticity of demand, right? Now, they are all part of the expressions. Price elasticity of demand is a percentage change in quantity by percentage change in price. That's the general idea for elasticity. Now, so this percentage change in quantity is expressed as the Q, which is the same as the change in quantity over the original quantity. Okay, that's the same thing. And if in terms of price, it is dP over P, which is the same as percentage change in price, the change in price over the original price P. Okay, so all we have just written is to represent this whole thing here. This change in Q and change in P is the same as the rate of change, isn't it? And in doing in writing it in a function form, for in the case of derivative, we use the something. So it's just the Q, okay? And this is the P. Is that okay? Right? So this is the percentage change in price, and this represents the percentage change in quantity. Now it says that it is percentage change in quantity over percentage change in price. So this is the same as the Q all over the P. Okay, so if you have this expression, we can divide two fractions. So we rewrite it, it becomes multiplication. So we have the Q times, and then this kind of like flips, rotates. So you now have P. Okay, all right. So this is like saying this is multiplying this and this is multiplying this. So all we've just done is to rewrite this expression as the Q over the P multiplied by P over Q. That's all. So we just want to have where we have the rate of change, on one side, and when we have the original prices on the other side. That's all that we did. And so we took them into the expression here. So this is the rate of change aspect. And these are this aspect here represents the original price and the original quantity. So you have a certain expression, P squared this here. So this portion here represents the derivative of this. So which is what we have here. So take the derivative of this, and this whole thing represents this whole portion here. Okay, so this whole portion of the expression. So this here is the derivative here, dq dp. Good. Now we are left with the original price and then the original quantity. We were given an expression which represents the quantity. This is this. So we have represented it here. And then we do not know the price, but we represent the original price with P. And so once we have this, this already is multiplying everything here. You know, this whole portion is multiplying this whole portion. So whatever we have, the derivative here is multiplying everything here. So what we just multiply this. We multiply this, and you have 2p squared or minus 40p all over this expression here. So this expression here, we can't do much about it anymore, but we can do a lot about it anymore because it's the way the function is. So this whole thing here is the derivative, or is the expression for finding the point elasticity of demand. Okay, so if we know at any price, once we substitute the value or that price into this expression, it should tell us what the point elasticity of demand will be. So we took an arbitrary price. Let's say, supposing the B part of the question says, if P equals 15, what will be the point elasticity of demand? So when P is 15, point elasticity of demand is minus 6. So let's say you can again something, maybe P is 30 or P is 40 or P is something. It would also be able to tell you what the elasticity of demand will be. Okay. All right. Any question? Okay. All right, guys. So please, I will end it here for us. Guys, last week, did we not do this? Or we didn't?
No, sir.
We didn't, right? Okay, you guys.
No, sir, we didn't.
Yeah, Tuesday was a holiday, isn't it? For you. So we couldn't meet on Tuesday. Yes. All right. Okay, so Edward Saforo, you have a question. Sorry, you have a hand raised.
So please, your slides. Can we have it?
You guys don't have the slides?
No.
Please ask your coach, because I have shared.
I sent the link to the slides. I shared it, sir.
They forgot it.
Okay. All right.
All right. Okay, and I've also shared the books that we're using, the recommended textbooks. I've also shared it with them, and then the course outline. So I think everyone has the information. Okay, guys. So yes. Yes, please.